So what we're going to be looking at today are permutations and combinations. Now, to talk about this, we're going to get into some formulas that use the factorial, well, it's a factorial operator. And it works like this. And there's a key on your calculator. If you have a scientific calculator, you'll see this exclamation point or something with an exclamation point on it. And that's what this means. It's the product of numbers 1 through n. So in factorial, and I'll do a concrete example, it's n times n minus 1 times n minus 2 times all the way to 2 times 1. So for example, three factorial is 3 times 2 times 1, or 6. Now, some more sort of advanced examples. Let's say we have 9 factorial over 6 factorial. Well, this will be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over, well, 6 times 5 times 4 times 3 times 2 times 1. So what we can do is cancel these terms. And that's going to leave 9 times 8 times 7, or 504. So questions about that? Now we're going to be doing some things with these quite a bit. Well, let me show you another one. Another one that's going to be important is with parentheses.
Oops, I missed. Oh, sorry. 9 times 8 times 7 is?
Oh, 504.
504. Okay.
Here, I'll wait for you to.
I got it. Is it 4 minus 3?
Oh, it's 9 minus 5. Oh, shoot. I'm sorry. Let me lower this. Let me fix my camera there. It should be 9 minus 5. My creative take on numerals. Now, the key thing with this, we want to perform the computation in parentheses first. So this is going to be 4 in parentheses factorial, and then we can drop the parentheses. And now we can compute the factorial. And so the answer is 24. So any questions about factorial? I have 2 other properties to show. So, oh, not example. So these are just going to be notes. The first one is 1 factorial is equal to 1. And the other is 0 factorial is also equal to 1. So these are going to be 2 properties to hang on to. We might encounter these as we do the homework problems. So now we're going to talk about permutations. And so permutations, these are arrangements, or here, I'll just do a singular. It's an arrangement of objects in a definite order. So it's an arrangement of objects in a definite order. And the key thing with permutations, and this is what's going to make them different from combinations, which we're going to see later, is that the order matters. So for example, if we have ABC, this is a different permutation from BCA, which is a different permutation from BAC, and there's other combinations we could do. But these are considered different permutations, and that's because the order of the objects is different. So we're going to derive the permutation formula. And so the formula is going to be this. This is the idea. We're looking at the number of permutations of n distinct objects selected k. So that means we're going to pick k of these objects. We have n, and we're going to pick k of them. So k is going to be some number smaller or equal to n. Usually it's almost always going to be smaller than n. So pick k of them at a time. So what this means, we can imagine this as drawing, like drawing a ticket, not like artistic drawing, but like we're pulling something out of a hat. We're drawing a ticket out of a hat. Drawing without replacement. So now this with and without replacement is going to become very applicable. So what we're going to do, I'm going to use an example. Make this a little more concrete. Let n equal 8, let's say, tickets. And each ticket has a unique identifier, like numbers 1 through 8. So we're going to draw k equals 3 tickets. So what this is going to mean, we're going to use the principle, or the counting principle. So this is going to be like a 3-stage experiment. So for the first stage, we have 8 tickets to pick from. So we pull a ticket out and we put it aside. That means for stage 2, there's 7 tickets to choose from. We pull out a ticket, put it aside. And that means for stage 3, there's 6 tickets to choose from. So this gives us the total number of permutations. Now, I'm going to do something. It's going to seem a little strange. I'm going to rewrite this using factorials. And this is how we get this formula. We can treat this as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1. And this is going to seem kind of odd, but if we, oh, sorry, not 6, we leave the 6 off there. But we'll see that, these cancel. And so we would still have our 8 times 7 times 6. So what we can do, we can write this as 8 factorial over 5 factorial. Or we can write this as 8 factorial over 8 minus 3 factorial. Oh, the factorial on the outside. And the idea behind this is we want to express this in terms of n, the total number of objects we can choose from, and then k, the number of objects we actually do decide to draw. And so this means we have a formula n factorial over n minus k factorial. And so that's how we get the permutation formula. Questions about that? So I'm going to write it up a little more formally. So we see the permutation n comma k, or the number of permutations is going to be this. So let's do some examples.
Oh no, I missed it. Okay,
Oh,
sorry.
so
P times n minus k.
it's p. Now this is kind of like a function of. Oh,
Oh, I see.
it's sort of like function notation. In a way, you could kind of think of this as a 2-variable function. Where instead of like f of x, it's f of x comma y, or in this case, p of n comma k.
Okay, I understand.
So it's kind of an interesting, I actually don't think I've actually looked at a graph of that. That'd be kind of fun to play with. Anyway. So let's look at an example. So let's say we have a golf team has 5 players ranked 1 through 5. So you can, so who knows why they're ranking them? Like it could be they have practice during the week, and whoever performs the best in practice that week will be like the number 1 ranked person, something like that.
Okay.
Now, if the total numbers or the total members of the team is 8, so there's 8 players on this team, but 5 are going to be ranked 1 through 5, like the top 5, and they would be, I guess, sort of the first pick for some competition. How many ranked teams of 5 are possible? So what we have here, the total number of players on the team is 8. And we're going to be drawing 5 at a time. And maybe this is just random. Maybe this ranking system is random. So we're going to have P of 8, comma 5, which would be 8 factorial over 8 minus 5 factorial, or 8 factorial over 3 factorial. Now again, you can compute this on your calculator, but you can also rewrite this as 8 times 7. Here, let me get a little more room. 8 times 7 times 6 times 5 times 4 times, and then that's 3 times 2 times 1, or 3 factorial. And so now you just have to compute. I'll bring in my calculator. We get 6,720, which is quite a few ranked teams. That's not trivial at all. Questions about that?
No.
All right.
Oh, I get it, because we stop at 3. Okay, I was just double checking. That's so cool. Okay, good.
Oh, sorry?
That's really neat. It's like it magnetic, like it tells it to stop at a certain point. I was trying to understand why. Silly, but yeah, that's cool stuff.
Well, it's a lot that you'd be surprised how many outcomes you can have. Now, here's another one. This one's a little more complicated.
Okay.
So 5 women and 4 men are seated in a row of 9 chairs. So how many seating arrangements squeeze that in there are possible. Now, we're going to consider a couple questions here. Now, how many seating arrangements are possible if there are no restrictions? On seating. So it could be first come, first serve, could be picking people by lottery. You have your ticket, you go in seat 1, your ticket go in seat 2. So the way this works, there's no restrictions. We're going to have a total population of 9, and we're going to choose 9. So what this becomes is n comma k will be 9 comma 9, or 9 factorial over n minus k, which is 9 minus 9 factorial. And there is for that 0 factorial is going to be helpful. That's just 9 factorial over 1. And then 9 factorial is 362,880. That's a lot of different arrangements for seating 9 people. Questions about that? So the next one, for part B, this is kind of an interesting one. And again, we're going to think back to our counting principle. Let's say we're going to do this. There's a restriction where women sit together. And men sit together. Now, in this case, we're going to look at this as basically, you could think of it as a 3-stage experiment. So first off, we have to decide which group we're going to seat first. And in this case, there's 2 options. Then, once we've decided on that, we can choose the seating of, say, women. And what this is going to be, you can think of this as P, so there's 5 women. So we choose all 5. or 5 factorial. Now, when we make the choice men or women, we could choose to either seat women first and then men, or seat men first and then women. Those are the two choices we're looking at. So we could have women seated first and then men. That's one of these options. Or we could seat men first and then women. And then for seating women, it's going to be 5 factorial. And then for men, same thing. So for this experiment,
I totally missed it. That's so funny. I didn't see the board up, and I was like, "Whoa, the force just turned into 5."
oh, sorry.
Okay, let me get this done really super quick.
No problem.
Okay, I understand. Okay, now you can change it.
So since we're sitting the groups together, we could say that stage 1 is we seat the women. So there's 5 factorial ways we could seat women. And then stage 2, we could seat men. Now, what we could be doing here is we might not actually be putting people in chairs. We could say, okay, all the women stand up, and we're going to arrange you into this particular order. And so the women arrange themselves into a particular order. And then we say, okay, all the men stand up, arrange yourselves into a particular order. And so the men arrange themselves into a particular order. And then finally, we have 2 options. Do we put the men at the beginning, or do we put the women at the beginning? And so we get a ×2 for our stage 3. And so when we do the math on this, what we'll get is 5,760. Any questions about that?
No, looks okay. So what you do is, I'm sorry, I'm just double checking really quick. So if you do the 5, how does this one go? It's 5, 4, 3. Or wait, it goes to.
So you do 5 times 4 times 3 times 2 times 1 times 4 times 3 times 2 times 1 times 2.
Beautiful. Okay, awesome. And then you, okay, I see what you did there. I was just making sure that it wasn't a division problem.
Oh, no problem.
Okay.
Now, there's another version of this. And it works like this. It's the permutation of indistinguishable objects. And so the way this formula works is this. So we have n objects divided into R groups. So for example, we might have something like this. Let's say n is equal to 9. R is equal to 3. And so we could have like A, B, 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 C, and C. Now let me change this a little bit. I'll make this a little bit different. So you have R is 3. We'll keep that. See, n is 12. Now we have 12 total objects. Now I'm going to call this group 1. And this group 2. And this group 3. Numbers 1, 2, and 3. And so what we're going to say is the number of objects in group number 1, we call this K1. It's going to be equal to 3 objects, 3 A's. The number of objects in group number 2, it's going to be K sub 2, that's going to be 4, because we have 4 B's. And then finally, the number of objects in group number 3 is K sub 3 or 5. So to recap, we have 12 objects divided into 3 groups, the A's, the B's, and the C's. The number of A's or group 1 is 3. The number of B's or group 2 is 4. The number of C's in group 3 is going to be the number 5. So what we're going to do, these are indistinguishable in the sense that the A's all look the same, the B's all look the same, and the C's all look the same. So the number of distinguishable permutations of n equals 12 objects. R equals 3 groups. Where K1 equals 3 identical objects are all A's. K equals 2. That's 4 identical objects are all B's. And K3 equals 5 identical objects are all C's. So what we're doing, we have these A's and B's and C's, and we're looking for distinguishable permutations. So a permutation that we can tell is different from another. And so the way we figure this out is we take the total number over K1 factorial times K2 factorial times K3 factorial, which will be 12 factorial over 3 factorial times 4 factorial times 5 factorial. We're going to make the note K1 plus K2 plus K3 is equal, not R, I'm sorry, it's equal to N. And I'll do a little explanation here of what we're talking about. So what's going on here? So what it is, and I'll go through some illustrations, sort of distinguishable versus indistinguishable. So you kind of see what we're trying to count. Is it okay if I erase?
Just the bottom part, I need, it's under, okay, so it was the note K1 plus K2 plus K3 equals N. Okay.
Got it. No problem. So what's going on is this. So we have, here's a permutation of these elements. It's an arrangement. So what we can do, we could switch these two A's, switch these two B's, and we could switch these two C's. And these are, after we make those switches, well, this is what we're going to get again. Doesn't look like anything's changed. So these are not distinguishable. They're indistinguishable. So these are going to count as one permutation, because we can't tell the difference between this one and this one. After we switch the A, switch the B, switch the C's, well, we get the same thing. But then let's say we have our first arrangement. And we switch these two letters and say these two letters. In fact, switching these two would be enough. But we're going to go the extra mile. Now, in this case, as we go from here to here, when we make our switch, now the permutations are distinguishable. So these count as two permutations. So what we're doing with this kind of complicated formula, and I'll go over an example to illustrate how it's used, but this kind of switching is not going to give us a different permutation. So these will count as the same one. But this kind of switching will give us a different looking permutation. We're going to get two. So what we want to count the different looking
Will you move the camera down just a little, please?
Oh, sure. Writing off the board. Oh, off the camera view, I should say. So we want to avoid counting permutations that look the same. And so that's what we're trying to avoid. So let me run through an example. If I'm erasing too fast, let me know. So let's say we have a 7 character password using the following letters. 1, 5, 5, in, u, in. Now this is supposed to be someone's address. So the question we're going to ask is this: how many different passwords are possible? So again, let's take a look at this. So So let's say we have our first password. We'll call it password number 1. And this will just be the 155 NUNN. Now to get password number 2, we're just going to switch some terms around. Let's say we're going to switch the 5s. We'll switch these 2 N's. And so when we make those switches, golly, look what happens. Nothing. Because when you enter this or this into your computer, it's the same thing as far as the computer is concerned. So this is really the same password. Typing this or typing this, you're typing the same thing. Your computer is just the same password. So nothing different there. But then again, let's say we do this. We start out with our 155 noon. And we switch, say, the 1 and the N, the U and the N. Well, now we do have, I'll abbreviate different passwords. So when it matters that when it's possible to switch elements around and nothing changes, you get the same permutation, that means we want to break out this formula. So we've got that same situation as before with A's, B's, and C's. So let's set this up. Any questions so far? All right. So we're still continuing with this example. So we're going to let the group 1 and we'll let group 1s be 1s. Now, here's our letters to start. The number of 1s is just 1, so K1 is equal to 1. Group 2 is the 5s. And how many 5s are there in group 2? Well, there's 2. Group 3 is the N. And the number of N's in group 3 is 3. And then finally, group 4 is the U's. And the number of elements in group 4 is 1. Now the total, you need n, so k1 plus k2 plus k3 plus k4, 1 plus 2 plus 3 plus 1, it's going to be 7 that equals n. So now we've got our k's, we have our n. Now we can compute the formula. How many unique passwords are there using 155NUNN? We take n factorial, k1 factorial, k2 factorial, k3 factorial, k4 factorial. So you have 7 factorial, 1 factorial, 2 factorial, 3 factorial, and then 1 factorial. So 1 factorial is just 1.
Right above it, it says K, and then it says 7 factorial. Okay.
Sorry.
Pretty good.
No worries. I got to watch how I'm letting this board sort of slide around. So I can rewrite 7 factorial. 7 times 6 times 5 times 4 times 3 factorial, 2 factorial times 3 factorial. And those cancel out. So 7 times 6 times 5 times 4 over 2 times 1. We can rewrite 4 as 2 times 2. 2 times 1 is 2. So I'm just doing sort of the slowpoke simplifications. So you get 7 times 6 times 5 times 2. That'll come out to 420. All right. So that's permutations. We have one topic left. And this is what's called combinations. So any questions about permutations?
Oh.
All right.
It was 420, right?
Correct.
And I'm sorry, did you just put equal or did you put n equals?
I put equals, just equals.
Just double check.
So the thing with combinations is this. Here, order doesn't matter. Here, order doesn't matter. So if you have ABC, that's the same as BCA, which would be the same as CAB. As long as they contain the same elements, these are all the same. Or the same objects. So let's do an example. Let's say we have n equals 5 objects. And then we choose k equals 3. So we're going to count permutations to start. So for permutations, and this is when order does matter. We'll get 5 factorial over 5 minus 3 factorial. So that's a number of permutations. So what we've done is we've chosen three objects. Now what we want to do is this. Every arrangement of these three particular objects we've chosen, now that we're talking about combinations, we're going to consider those the same type of combination or arrangement. So every arrangement of these three chosen objects we group as one combination. So again, ABC equals CAB equals BCA. We all consider those one combination. So I'll just kind of give an example. So ABC, again, we've seen this one, but BCA, CAB, and there's others. Let's see. BAC. We have.
Now they do equal each other?
They do. Where did BCA?
Okay.
CBA. There's one more. Let's see if I can figure it out. CB. Should be one more, and I'm missing it. ACB. There it is. So these 6 permutations are one combination. So when we've chosen 3 elements, we can get 6 permutations out of these 3 elements, but they're only going to count as one combination. So by counting permutations, we'll overcount by 6. Well, let me be careful I word this, but we overcount permutations. Sorry, that doesn't seem to really be very helpful. Basically, I'm going to say is we overcount. We don't want to count the permutations. We want to count the combination. So the way we're going to do this is we're going to divide by 6, which we can write is 3 factorial. Any questions about that? I'll admit, I think it's a little. Any questions, let me know. But basically, we're repeatedly counting the same combination. And we've counted it, end up counting it 6 times when we only need to count it once. And so to solve that problem, we're going to divide by 6, but we can write that as 3 factorial, or the number of elements we draw factorial. So what this means is we take P 5, 3, we divide it by 3 factorial. And so we get this. And this is the number of combinations with 5 total objects and 3 being drawn. And so what we get, the number of combinations of K objects drawn from in total. So we get C in K is in factorial k factorial and minus k factorial. Questions about that? So let me do an example. So these are situations where ranking doesn't matter, order doesn't matter. And that's kind of the big thing with these problems is when the order doesn't matter, you're going to be looking for combinations. When order matters, you're going to be looking for permutations. So let's say we have this. Say an ER at a hospital has 11 nurses. Five nurses are chosen as a team for night duty. How many teams are possible? So the key thing here is there's no order of nurses. So you're not going to have nurse 1, nurse 2, nurse 3, and then if you switch nurse 1 and nurse 2, you have a different kind of order. It's just going to be groups of 5 people. The order those 5 people are in doesn't matter. So we're going to use the combination. Now, how many do we have? We have 11 total, and we're choosing 5. So these are going to be combinations. We have 11 factorial, 5 factorial, 11 minus 5 factorial. Five factorial, 6 factorial. And so we can write this as 11 times 10 times 9 times 8 times 7 times 6 factorial over 5 factorial times 6 factorial. And again, we can cancel those 6 factorials. (11 times 10 times 9 times 8 times 7. And so what that's going to come out to, we can expand this out. We get 462. So that's the number of 5 teams of nurses we can have that are totally different teams, not based on order, but by on who's on the team. So the last question I want to do, it's along these lines. It's kind of a complicated one, but it's a good one. And one of the things you're going to get when you're dealing with combinations and permutations is cards. You're going to be doing things with a deck of cards. So a standard deck is 52 cards. And 5 are chosen. So what we want to find out, how many combinations, before we get to part A, let's go, how many combinations are there of and then we can put in our part A. 2 kings, 3 queens. So what this is going to be, this is a multi-stage experiment.
Okay, cool that you're showing us this now, because I was looking at one of the other ones and I was having a difficult time trying to figure these ones out.
No problem. So the first stage, so stage 1, we need 2 kings. Now in a deck of cards, there's a total of 4 kings. And again, the order doesn't matter.
Will you
So
move it up a little?
Oh, sorry, I'm sorry.
Okay.
Oh, there we go. So stage 1, we're picking the 2 kings. And so the number of ways we can pick the 2 kings is 4, choose 2. That's how we can read that. And then in the second stage, we're going to choose the 3 queens. And there's 4 queens in a deck. We're going to choose 3 of them. And again, there's no order to these queens, so we're just going to do combinations instead of permutations. So we'll get 4 factorial, 2 factorial, 4 minus 2 factorial times 4 factorial, 3 factorial, 4 minus 3 factorial. So we get 4 factorial, 2 factorial, 2 factorial, and this means 2 factorial times 2 factorial, you know, with little times in there, times 4 factorial, 3 factorial times 1 factorial. And if you simplify this down, you're going to get 24. So there are 24 ways of choosing 2 kings and 3 queens. Questions about that?
No.
Let's see. Now let's do another one. Let's say, now we're still going on this one. We have part B coming up. How many combinations are there of 5 hearts? Now, there are 13 hearts total. And we're going to choose 5 of them. And so since the order doesn't matter, we just want hearts. We don't like want an order of hearts, like 2 of hearts, 3 of hearts, things like that. We're going to ignore the order. Just want 5 hearts. 13 factorial, 5 factorial, 13 minus 5 factorial, or 13 factorial, 5 factorial, 8 factorial. And if we hammer this out, if we simplify it down, get 1,287 combinations of 5 hearts. Now, part C is an interesting one. This is kind of a fun one. So any questions about that? So now we want to ask, how many combinations are there of 5 cards of the same suit? Well, first off, there are 4 suits. Hearts, diamonds, spades, clubs. So what we know is this. The choose 5 cards of the same suit. We know this from part B. Oh, excuse me. Excuse me. Well, from part B, there's 1,287 combinations of 5 cards of the same suit of hearts. So we've already chosen the suit, and this is kind of the key thing here. We've already chosen the suit. So in part B, we've done that. Now this becomes a 2-stage experiment. So stage 1, we have to choose the suit. Now that's what's different in part B. In part B, the suit was already chosen. It was hearts. But here, we have to choose the suit. So how many possible outcomes are there for choosing a suit? Well, there's 4 suits. So that means there's 4 possible outcomes for choosing a suit. And then after we've chosen the suit, then regardless if the suit was hearts or clubs or spades or diamonds, we then choose the 5 cards from that suit. And it doesn't matter if it was hearts, diamonds, spades, or clubs, the number of possible outcomes or the number of combinations for choosing those 5 cards from the same suit, 1,287 were our C13, 5. Because there's 13 cards per suit. We're going to choose 5 of them. We're looking for combinations. So this will be 4 times 1,287. And that comes out to 5,148. So questions about that? So that's it for section 12.2, and that's it for chapter 12. It's just going to be those 2 sections, and then we'll do some work in chapter 1, and then yeah, we're starting to come up to the end here. So again, if any questions, let me know. Other than that, have a wonderful afternoon.
Also, okay, I just wanted to double check really super quick.